we have Will Merrill here, who is currently a PhD student at NYU and also is supported by AI2. And yeah, his research covers a lot of like language models and computational power of transformers and complexity theory. And today he will present to us his new work on the illusion of state in state space models. Thank you for being here today, Will, and you can take it from here.
Thanks, Lena. Yeah, so this is going to be a talk about a new paper that we haven't put out on ArXiv yet, but it should be out in the next couple of days. And it's a bit of a detour away from transformers towards state space models, which are kind of this new architecture that has probably come closer compared to any other architecture to like closing the gap to transformers for language model. And this is joint work with Jackson Petty, who's another PhD student in my lab at NYU, and then Ashish Sabharwal at AI2. So the context for this work is that we, Ashish and I, had thought a lot about transformers and like the limitations of transformers in terms of circuit complexity. And kind of one of the main results that's emerged about this is that transformers can only solve problems in the complexity class called TC0. And one thing that follows from this, which has been identified, for example, in the shortcuts to automata paper, which was also presented here, is that this implies limitations for state tracking. So in particular, if you want to give a transformer a sequence of chess moves and ask the transformer, is it possible to compose these moves and say what the final board state is? That turns out to be an NC1 complete problem. And that means that likely transformers cannot express a solution to it because they can only express functions in TC0. Similarly, if you have a code evaluation task where you write down some Python code and you want the transformer to be able to tell you what the state of all the variables in the code is after the code's been run, that also turns out to be NC1 complete. And therefore, we know the transformer shouldn't be able to express a solution to this kind of state tracking either. So the intuition behind these limitations is that basically transformers can only view the sequence of inputs that they get through attention, not through any kind of like recurrent mechanism. And therefore, these state tracking tasks, which are kind of easy to decompose recurrently, are hard for transformers to express. So a natural question arises then. We know that these tasks are kind of limiting for transformers, but what about state space models? So state space models, if you're unfamiliar with them, are designed to kind of look like RNNs, right? They have this recurrent update that is basically the same as a classical RNN, except there's no nonlinearity. And therefore, at least intuitively, it seems like these models might be able to solve these state tracking problems that we know transformers cannot express solutions to. And if this were the case, it would be quite interesting because it would be a point in their favor over transformers if we think that state tracking is something that models should be able to do on real tasks or for processing natural language. So in this paper, we kind of evaluate this question of whether state space models are better at state tracking than transformers. And the first thing we do is we are going to draw an existing theory to rigorously formalize what hard state tracking is and what it means to kind of solve hard state tracking. And then we're actually going to show that state space models cannot express hard state tracking, hence the title, The Illusion of State in State Space Models. So in theory, we actually proved that state space models like transformers can be expressed in TC0. And this means by the same reasoning as for transformers, they can't express hard state tracking. And then in practice, we do a fair amount of evaluation where we kind of compare canonical state space models and transformers and train them on representative hard state tracking tasks. And in both cases, we see that basically they perform worse than an RNN does. And crucially, they need kind of a depth that grows with the length of the input sequence. And finally, we actually propose a minimal extensions to state space models that theoretically can express state tracking. And we show in practice that this model actually performs very well on the synthetic state tracking tasks that we evaluated the transformer and state space models on. So this is a minimal change that is still kind of pretty parallelizable, that gives much greater expressive power compared to the other architectures. So also feel free to interrupt me whenever. Maybe I don't know what the best way to signal that is, but happy to take questions at any point. So I'm going to move on to the first section. So this is kind of the background about what I mean by state tracking and how we formalize this. So I already showed you some examples of state tracking. One was this kind of chess composition of moves task. Another one is code evaluation. And both of these are like somewhat synthetic, but also, tasks that could reasonably show up in something, in what a language model is asked to do. A third example of where state tracking really shows up in natural language processing is if you think about what it means to actually just like evaluate natural language, there's a lot of semantic theories that actually look a lot like state tracking. So in particular, one of these kind of popular theories for formalizing like entity tracking in natural language is called file card semantics. And the idea there is basically, as you process a document, you maintain a file for each entity, and you kind of update the contents of that file as you learn more about different entities or as entities change over time. And this is kind of naturally a state tracking task where there's some state associated with each entity, and the goal is to kind of compose all the sentences that you've read so far and figure out what the kind of cumulative state is. And actually, this entity tracking thing is not, it's like one example, but this is really like a fundamental, if you look at semantic theory in linguistics, this is like a fundamental part of what it means to kind of evaluate the semantics of a text. And therefore, it's kind of a fundamental part of language understanding. So this is a bit of a brief aside, but kind of classical formal semantics, if people here are familiar with formal semantics and linguistics, says that the meaning of a text is its truth conditions. So in other words, semanticists under kind of classical formal semantics would say that every sentence has a meaning, which is a function from a set of worlds to 0 or 1, or equivalently, it's a set of worlds that make that sentence true. This is kind of like a model theoretic notion of semantics. And then if we have these kind of sentence meanings, then the meaning of a text is just the intersection of those sentence meanings. So we have meanings, phi 1 through phi n, and we just take the intersection across all of those. So that's classical semantics, but it turns out that this is kind of not sufficient to capture many types of phenomena in natural language. So one example is when you have pronouns that can be bound to different entities and change over time. The order of these phi's actually matters a lot, right? Because maybe phi 1 introduces the referent of a pronoun, and then it matters that phi 1 came first, but intersection can't capture that order sensitivity. So actually, like modern semantic theories have generalized this kind of classical definition to something called dynamic semantics, which says that the meaning of a sentence is a world update relation. In other words, every sentence has a meaning M, which is a function or relation from worlds to worlds. And then the meaning of a text is viewed as kind of composing these meaning operators to get a new function that describes how the overall text kind of acts as an operator over the world. So this is a lot of kind of formalism. It's a bit, orthogonal from the main part of the talk. But the point here that I want to emphasize is that if you take this dynamic semantics view of what it means to kind of understand language, it really is that understanding language is a state tracking problem, where all of these kind of M's are different operators that update the state of, the world, and the goal is to kind of compute their like composition. So that's a bit of why we kind of care about state tracking. We can look at these specific tasks like chess or like code evaluation and see that those are really state tracking problems. And then I kind of gave you this kind of more linguistic argument for why state tracking is something we should care about. But what do I actually mean by state tracking, and how are we going to formalize that in this talk? So we can think about state tracking as what's called a finite monoid word problem in algebraic formal language theory. So a monoid is just a set with some kind of abstract operator that is associative and has an identity 1. And then a word problem is defined with respect to a monoid. And the way it works is that the input is a sequence of elements in the monoid. And the output is just their product under this dot operator. And this looks a lot like what I showed you on the last slide, where basically you can think about each sentence having a meaning. And the goal of kind of evaluating a text is to compute the product of the meanings of all the sentences. You can also think about these M's as like chess moves. And then you get as input a sequence of moves, right? And the goal is to say, what would be the cumulative effect if you apply all those moves in sequence? That would be like what this output would represent in the chess case. So this is like a general kind of framework to describe different state tracking problems. And basically, depending on how we set the monoid, we're going to capture a different type of problem. And depending on the underlying complexity of the monoid, this problem may be harder or easier. So the difficulty of the problem depends on basically which monoid we're talking about. So there actually is a nice theory about how the complexity of this monoid word problem changes depending on the monoid. And one of the kind of key results is that there's an algebraic property called solvability that determines whether the monoid is either computable in TC0 or NC1 complete. So it turns out for finite monoids, there are kind of two possibilities. And I guess, yeah, it's easy to kind of characterize which one is true depending on this algebraic property. And because we know that basically transformers are in TC0, and I guess the new result we have in this paper is that state space models are in TC0, this basically automatically tells us if we see that a monoid is NC1 complete using the algebraic structure, then we know that transformers and state space models shouldn't be able to express a solution to the word problem for that monoid. In other words, they shouldn't be able to solve that state tracking problem. So what are some examples of hard state tracking? It turns out there's one canonical monoid that is like very simple that is NC1 complete. So again, NC1 complete means hard here. And it's called the S5 or permutation composition over 5 elements monoid. So an example of how this works is we have like 5 bins, and then we place objects, kind of in some of the bins, and then we specify swaps or general permutations or just transpositions over the bins. So for example, we might say swap hat. I don't know why it says hat here. It should be box, but swap box 1 and box 3, swap box 3 and box 2, and then at the end you have to answer a question like, where's the apple, or where's the brain? Interesting. So that's an example of how this monoid works. And this is kind of this one of the smallest NC1 complete monoids, which is why it's an interesting testbed. We can actually also embed this monoid into other problems. So the reason why I know that chess is a hard state tracking problem, for example, is because you can come up with a chessboard that encodes this S5 monoid via reduction. And what that means is there's like a sequence of moves over the board that basically correspond to all of the transpositions in the box monoid. And therefore we know that this chess thing is like basically at least as hard as S5. So that's like what hard state tracking looks like. The kind of running example we're going to be using from now on is this permutation composition task. And by extension, that kind of code evaluation in chess can be kind of, that task can be reduced to code evaluation in chess. So therefore, those are also hard state tracking. But it turns out that there's also examples of state tracking that intuitively might feel hard, might feel like they require kind of this recurrent decomposition of the task, but that we can show are actually kind of easy. So one example of this is S4. So what if we go back to that task from the last page, but we have 4 bins instead of 5 bins. It turns out that for very non-trivial reasons in algebra, so related to like Galois theorem, this is actually not hard, unlike S5. And that's, I mean, completely not obvious to me. Another one is the chess hardness result. So I told you on the last slide that chess is NC1 complete, but it turns out that this actually depends on the notation we use to write down the chess game. So if we write it down in non-standard notation where you denote moves by like source and target position, then it's NC1 complete. But if you instead wrote it down as like queen, comma, target position, like where the move goes to, that turns out to be in TC0. And I think that's really hard to see at first glance. It turns out that actually in this bin task, so we took this from paper Kim and Schuster from 2023. And while this bin task does actually capture like S5, the way that I wrote the prompt on the last slide, it turns out that the original way they formatted it in this paper actually makes it not hard. So if you see here, the way they describe the updates, they say like move the book into box 2 rather than like move box 1 into box 2. And that makes it kind of analogous to the queen E8 formatting in chess, as opposed to the E5 E8 formatting in chess, and actually turns out to make it not hard or in TC0 as well. So I think the takeaway here is that you actually need theory to tell you what hard state tracking is and what state tracking is fundamentally kind of recurrent and not kind of solvable via some shallow, decomposition. Because it turns out that a lot of these things, like if you just kind of set it up naively and don't check, something that seems like it should be kind of hard state tracking might actually not be.
A quick question.
Yeah.
So is the kind of labeled version where that says like queen to E8, for instance, is that not hard because there's like some like shortcut rule where you can just look to the last place the queen moved to see where it is?
Yeah, exactly. So if you think about doing it with a transformer, basically it's a little bit involved, but the intuition is like you can always kind of look back at the last time the queen was moved and find what position it was moved to. And that makes the task much easier. So you can think about it as kind of like you're giving your transformer a like recurrent hint in the input. You're basically augmenting the input with like some kind of state that it can kind of use rather than like computing that recurrent state itself.
Cool, thanks.
Yeah. Okay. Okay, so that's, anyway, this, I think, reiterating what I said before, I think this slide basically captures, or it kind of shows via a couple examples why it matters to focus on like the hard state tracking case and not just like an intuitive example of what seems to require state tracking. Yeah, so basically we formalize state tracking via this monoid word problem taken from algebraic formal language theory. And the kind of natural kind of case study that we're going to focus on is this S5 task, which other hard state tracking tasks can be reduced to. And it's kind of like a simple example of what hard state tracking is. And yeah, basically that's this. I'm gonna move on to the theoretical results now. So basically the main results that we show here is that state space models can only solve problems in TC0. And basically the theorem is this. So the first theorem is any linear state space model can be computed in TC0. We then have another theorem that says that the S6 model, which is the architecture behind Mamba, you may have heard of this new kind of model that just came out, can also be computed in TC0. And the reason why we have the second theorem is just because S6 actually generalizes the original linear state space model in a particular way. So again, the main implication of this for the purpose of this paper is that state space models can't solve the S5 state tracking problem. Apologies for the S5, S6, S4, all these different things appearing in this paper, but S5 is the task, and then S4 and S6 are two types of state space models. But yeah, beyond the state tracking implication, these results also just generally show that state space models can't solve graph connectivity or other hard problems outside TC0, under the assumption that TC0 doesn't collapse to higher complexity classes. So I want to talk a bit about the proof for this and why this is surprising. So just to remind you, like state space models look a lot like RMNs, except that they don't have a nonlinearity. And we know that these recurrent models can easily express the S5 state tracking problem, because all they need to do is really encode like a finite table that takes the previous input and then the previous state and the current input, and then just computes a finite table of those two things. So why is it that this nonlinearity really matters so much, and that when you remove it, it starts to fall apart? So to understand the proof, it helps to kind of unroll the state space model. And because of the linearity here, we can actually rewrite this as a summation over different terms, like the following. And once you do this, you can see that this is really like a quite parallelizable thing, right? If you can compute all these terms in parallel, then you can compute a summation of those terms, because like iterated summation is in TC0. And that means that you should probably be able to compute this function in TC0. So in fact, the last piece we need is just the fact that matrix powering is in TC0. So the fact that we can compute these a to the I minus j factors in TC0 basically tells us that all of these individual terms should be computable in parallel. And then once those terms are computable in parallel, it's possible to aggregate them by just taking a summation over them. And that's essentially the proof idea. It's very simple. So yeah, basically the conclusion of this is that the state can be computed in TC0, and it's not hard to show that the output of the state space layer, which is basically a linear projection of the state, can also be computed in TC0. And another way to kind of think about this intuition is that, if the way that we're computing the hidden state is by summing, then this is going to basically be it's going to be commutative. Like you could rearrange these terms however you want. And something about that intuitively maybe suggests that, we're not going to be able to express arbitrary state updates. So to reconcile this with past work, basically one of these lemmas from the original state space paper actually gave a theoretical argument that linear state space models could express, or at least approximate, arbitrary recurrence. So here's the statement of the original lemma. Sorry, it's a bit blurry, but this kind of theoretical argument that state space models could kind of approximate arbitrary recurrence relied on infinite depth of the model. So in other words, the way their construction was working was they had like an infinite series of different layers, and they were using the residual connections to kind of add correction factors, I guess, to kind of approximate any arbitrary state function. But with a fixed number of layers, which is the regime our result is operating in, we see that actually there is kind of a separation between the state space models and between arbitrary RNNs. So that result actually relied quite heavily on the infinite layers, and in the fixed layer case, there's a difference. So that's for now the end of the theoretical results. I'm now going to talk about the empirics a bit. So basically, we want to test these word problems and see how the different models do. And the reason for this is, I guess, all the results I talked about so far are kind of worst case results, where we showed that in principle, the state space models can't express the S5 word problem, but we don't know what happens for fixed sequence length, or how large the sequences need to be in order for this worst case guarantee to start taking effect. Yeah. So we basically are going to use 3 synthetic tasks to try to evaluate this, which are word problems for monoids of different complexity. So the first one is Z60, which is basically like addition over the integers mod 60. And this is a simple commutative group. So we expect that all of the models should be able to learn this fairly well. And then the next group we're going to look at is A4 cross Z5, which is a non-commutative but solvable group. And sorry, just to clarify, a group is a special case of a monoid. So when I switch from monoid to group, you can think about these as monoids as well. But yeah, A4 Z5 should be maybe a little bit harder than Z60, but technically it's still solvable. So, it's not NC1 complete to solve the word problem. And then finally, the third group we look at is A5, which is the smallest non-solvable subgroup of S5. So S5 has 120 elements, A5 has 60 elements, and we just chose to look at A5 because it's smaller and still just as hard. So all these monoids are matched in their group size, which is why Z60 is 60 elements, A4 cross Z5 is also 60 elements, but they vary crucially in the algebraic complexity. One is commutative, one is solvable, and one is non-solvable. Okay, and then the way that we train these models is on a kind of what we call a cumulative product tagging task. So the input is a sequence of random monoid elements, and then the output is a sequence of cumulative products. So this looks kind of a lot like so for example, at the first token, we want to predict M1. At the second token, we want to predict M1 times M2, and so on, as we go on through the different tokens. And the reason we frame it this way is because it's basically the word problem task, except that, we basically are giving the model more supervision at every token by making it the tagging version of the task. And then the models we look at, as a baseline, we look at a randomly initialized RNN. And this model should be pretty good because we expect if the architecture is truly recurrent, it should be able to do state tracking quite well. And then the second model we look at is a randomly initialized transformer. Because the transformer is expressible in TC0, we expect the transformer to not be able to solve these tasks. And this gives us kind of a baseline for what failing should look like. And then we also look at randomly initialized Mamba, which is an example of a state space model. And also S4, although I think I might have forgotten to add the S4 results here, which is another state space model, and basically compare these state space models to the RNN and the transformer. And then the question that we're going to ask is basically, what depth is required to learn the word problem to 90% accuracy as a function of the input sequence length? So we expect that as the input sequence length gets longer, this required depth will grow. And Jackson, my co-author, has some past work on this, on basically like the role of depth in semantic parsing with like transformer language models, where basically in that work they found that the kind of depth has diminishing return as you if you're doing semantic parsing of like short sentences, past a certain point, increasing the depth doesn't improve performance that much. But here we kind of expect that this task really fundamentally requires depth in a way that maybe semantic parsing for like bounded late sentences doesn't. So we expect to see like, depth is more important than in that work. Okay, so here's the first set of results. And the way to read these plots is the x-axis has sequence length n, and then the y-axis shows the minimum number of layers needed to get 90% accuracy on the task. So in all cases, you can see the green line, which is the RNN, basically only needs one layer to get basically 90+% performance. And I think, in fact, it's basically perfect. The transformer, on the other hand, on Z60, we get really good performance with just one layer, meaning it can kind of solve this commutative word problem with just one layer. But for a more complex group, either A4 cross Z5 or A5, we see that you know, you need more than one layer, and the number of layers kind of grows with the sequence length. Similarly, for Mamba, we see that 1 or 2 layers seem to work for Z60. Maybe for some reason, actually, the model does need more layers here. Although for S4, which again, I don't have these results in the slide, but we actually saw S4, a different state space model, pattern more like the transformer and didn't have this little bump here. So we're not quite sure what that was about, but by and large, still needs less depth than the other groups. And then, for A4 cross Z5 and A5, we see that it's like somewhere in between the transformer and the RNN as far as the number of layers that it needs. Yeah, I guess I just said this. So I guess to summarize, the main kind of takeaway here is that the RNN kind of works perfectly on all the groups, no matter the sequence length. And then for transformers and Mambo, we get kind of depth dependence in the more complex groups. So a couple points to discuss here. So one, the fact that the RNN perfectly learned to solve these word problems with one layer reflects that the RNNs are basically truly recurrent, and they actually don't need, basically they can express the simple factorization of this problem in terms of recurrent updates. And another expected thing was that the transformers and state space models required increasing depth for the longer A5 sequences, so the hardest group, which is NC1 complete. But why was it the case that they also required depth to increase on the solvable group A4 cross Z5? Because here we don't have a theoretical reason to think that they shouldn't be able to express this group. So there are two. This is not like inconsistent with the theory, but we aren't able to pin down between the two potential explanations. So one explanation is that we don't know that transformers and state space models can express all solvable groups with constant depth. We just know that basically the one directional version. We know that if a group is not solvable, then transformers cannot express it, but we don't know, the other direction. So this could maybe be an expressiveness issue. Maybe these models just can't express, a solution to the word problem. On the other hand, it could also just be something about learnability. And we don't have a way to kind of distinguish these at the moment. I'm noticing a question. Let me go back to this real quick. Did the Gödel theorem always require infinite layers? Or is it that arbitrary approximation scales with layers? Maybe I'll take this at the end just because I've moved on from there. Sorry. Maybe ask after the talk. Okay. So that's the empirical results. And then finally, I'm going to move on to the next section of the talk, which is basically a minimal extension to state space models that can track state. So basically, based on these results, we've seen that current transformers and state space models can't express or learn certain hard state tracking problems, but could we change them minimally so that they can? So based on in our past work on transformers, we kind of conjectured this inherent trade-off between parallelizability and state tracking. And specifically, what that trade-off said was that if you want constant depth parallelism, in other words, if you want your model to be computable with a constant depth computation graph with respect to threshold circuits, then you basically are not going to be able to express any functions outside of TC0, and therefore you won't be able to express NC1 complete state tracking. However, one thing we didn't consider when we kind of made this claim was that maybe constant depth parallelism is too strong. Maybe in practice, it's sufficient to have log depth parallel models. In other words, models that can be computable in NC1. and gain greater expressive power. And like that would be practically, parallelizable enough for people training large language models. So kind of a revised question is, can we have like some kind of model in NC1 that's an extension of the the original state space models that is kind of practically easy to parallelize and also can express hard state tracking. And one way to do this is basically we can make the transition matrix input dependent in the state space model parameterization. So before there were these two transition matrices A and B, and now we're just going to let the A matrix depend on the input. And because the input is kind of like, there's a finite number of options for the input, we can basically just let this be any function of the current input. And it turns out that, this is all you really need in order to be able to solve some NC1 complete problems. So why isn't this in TC0 anymore? So if you remember the last kind of proof sketch I gave you, I said that basically we could rewrite the state space model in a kind of convolutional form or a summation form. And then we could conclude that the summation of terms was in TC0. The reason why that worked is because this product here simplified in when A was fixed to a matrix power. And now what we get here is like a matrix product where we have a sequence of different matrices and we need to kind of compute their product. And it turns out that, computing products of matrices is not in TC0. And to see why, you can think about these matrices as representing like the transitions of a finite state machine. And if you want to compute their product, that's kind of equivalent to saying whether the finite state machine recognizes some string or not. It's at least kind of, close to that problem. And we know that like simulating automata is not in TC0. So that's like one way to see this connection. And yeah, so basically you can use this product also by that idea to like encode the transition monoid for an arbitrary DFA, which is NC1 complete. So this is really much more complex than if you don't allow A to depend on the input. One thing that's interesting here is that B actually, it doesn't matter if B can depend on the input. And some of these state space models like Mamba allow B to be input dependent, but they don't really allow A to be generally input dependent. So it's almost like, they chose this other parameter, probably for like practical, implementation reasons. That doesn't really matter from an expressivity standpoint, but if they had chosen the other one, it would have, kind of enhanced the power of the model. So based on this, like this is kind of a simple argument for why this thing is a good idea from an expressivity standpoint, but is this actually practical to do if we wanted to like, propose a new architecture, a new version of a state space model? So I think there's like at least two concerns besides expressivity that also matter here. So one is like how this impacts optimization. Maybe like if we allow this matrix to depend on the input, it somehow makes it harder for the model to learn. And that would be like, kind of an issue. Another potential issue is parallelism. So we know that this extension of the architecture theoretically kind of decreases the parallelizability from TC0 to NC1, but does that actually, translate to like making it slower on actual hardware, which is a bit of a different question. So to evaluate this optimization question, we basically just ran an experiment where we compared S4, which is kind of a simple state space model, to S4 augmented with input dependence. So we basically changed the A matrix to be input dependent. And what we found is that, S4, sorry, the order of the groups is reversed here. The right one is the easiest one, Z60. So here, like, both models get perfect. Like they only need one layer in order to solve the group as the sequence length grows. But for the harder groups, whereas S4 kind of patterned like Mamba, where like, you need more layers to handle longer sequences, one layer was enough with input dependent S4. So basically, it can learn to operate like an RNN, even though it's, yeah, it can learn to operate like an RNN. And then the second point that, was somewhat concerning about this and maybe would make us question whether this is practical is the parallelism. So is it possible to actually implement this input dependence and maintain like, an efficient implementation? So in theory, again, we have a slight kind of decrease in parallelism in the sense that whereas S4 would be in TC0, adding the input dependence puts it in NC1. But in practice, we can still have a hardware implementation of the state space model that has logarithmic depth. So the way to do this is basically you need to like compute this product of matrices using a binary tree and kind of, compose pairs of neighboring matrices together in an efficient way. And this should be possible to do, although, it would require doing some GPU programming or writing some CUDA kernels or whatnot. But one point to emphasize here is that actually, in practice, the S4 model also is implemented in this way. So even though S4 is technically in TC0 and has a constant depth, threshold circuit that computes it, in practice, when we implement it on actual hardware, it's implemented using and OR gates, and therefore it's implemented using an algorithm called scan, which computes the state using this convolutional decomposition, basically using the same idea, using some kind of binary tree that adds kind of pairwise elements. So if we just apply that same algorithm, but with matrix multiplication, it actually should be like similar in terms of the complexity, but just a little bit more complicated to implement, maybe. Okay, so I'm just going to wrap up.
Question in the chat.
Yes.
David is asking, is AXK a diagonal matrix though? Practical SSMs usually impose restrictions onto the matrix A such that it can be efficiently used over long sequences. A is not an arbitrary matrix.
Yes, this is a very good point. So actually, if you make A a diagonal matrix, you don't get more expressive power. So let me try to give an intuition for that. So here, if we make A diagonal, then this product here basically simplifies to computing the element-wise product over vectors, over a sequence of vectors, rather than over a sequence of matrices. And the element-wise product of vectors is basically just, the element-wise product of scalars in parallel. And that's actually known, like iterated multiplication of scalars is in TC0. So this whole thing would become implementable in TC0 if we impose the constraint that A is diagonal. In practice, you're right that like at least S6 and S4D both impose this diagonality condition. I think the original S4 actually doesn't. But yeah, to get the greater expressive power, you do need more. You do need this non-diagonal transition matrix. And that is like probably, I guess like asymptotically in terms of like, is the computation graph constant depth or log depth? It doesn't really matter. But in practice, I guess in terms of the amount of memory you need to keep around, having diagonal matrices does just make everything like more efficient and easier to work with. So that is definitely something that would be lost about if you wanted to use this higher expressivity model. Any more questions? Or okay, I'll just move on to the conclusion, then we can open it up. So the main result from a theory point of view here was that basically we showed that state space models can only express functions in TC0 like transformers. And if we think about this in the context of state tracking, this shows that their statefulness, which if you look at the architecture kind of jumps out at you, that they can compose these kind of recurrent state updates, is actually kind of an illusion. Because even though they look recurrent, we can prove that they can't express hard state tracking. And empirically, when we evaluate them on hard state tracking, they do much worse than RNNs. And this is evidence against one argument for state space models, which is that they maybe can express recurrence, or that they are kind of more recurrent than transformers. I mean, that's obviously not the only argument for state space models, and there are other arguments that, maybe are even, more important, like the fact that they have constant time inference. And yeah, but it also, I think, motivates extensions to the state space models that could possibly have greater expressive power than both the current state space models and also than transformers. And based on kind of the the fact that state tracking, at least to me, it feels like it's a really central problem in a lot of like in both these synthetic cases, like evaluating code, but also just for like dialogue tracking. I think it would be like really promising if we had models that could have these greater capabilities for state tracking. So yeah, thank you.